Now we're stepping to regularization in neural networks, and this is where things get even more exciting. Because if you thought overfitting was bad in regression models, just wait until you see what happens in deep learning when you don't apply regularization. Let's set the stage. Imagine you're training a neural network to recognize handwritten digits, kind of like the ones banks use to read checks. You collect thousands of images, label them, and build a deep neural network with multiple layers to classify the numbers. You train it on your dataset, and the accuracy starts shooting up 80%, 85%, 90%. Eventually, it reaches 99%. You're thinking, I've built a masterpiece. This model is a genius. But then you test it on new images, and suddenly the accuracy drops to 65%. What happened? Your network didn't learn how to recognize numbers. It memorized your training images, every single pixel pattern, every little noise variation. It stored them all like a giant lookup table instead of understanding the actual shapes of digits. And that, my friends, is overfitting at its worst. This is exactly why regularization is absolutely critical in neural networks, because without it, deep learning models memorize the training data instead of generalizing. Neural networks are powerful, but they have a major weakness. They have too many parameters. Think about it. A deep learning model with millions of neurons and connections can easily learn every little detail in the training data, even the ones that don't matter. And the result? It performs amazingly well on training data. It fails miserably on new data. This is why regularization is even more important in deep learning than in simpler models like logistic or linear regression. Regularization in deep learning is a bit different from L1 and L2 in regression. We use techniques specifically designed for neural networks to stop them from memorizing everything. Here are the 4 most common methods used to regularize neural networks. Dropout is one of the most powerful and widely used regularization techniques in deep learning. Here's how it works. Imagine you're training a basketball team, and every time they practice, you randomly bench different players. One day your star player sits out. The next day, another one is out. This forces everyone to learn how to contribute instead of just relying on a few key players. That's exactly what dropout does to neural networks. During training, it randomly drops neurons from the network, forcing the model to learn redundant patterns instead of memorizing specifics. By the time training is done, the model has learned robust, generalizable features instead of just overfitting to the training data. Just like in linear and logistic regression, L1 and L2 regularization can also be applied to neural networks, except here they're applied to the weights of the network. One regularization forces some weights to become exactly zero, simplifying the network and helping with feature selection. L2 regularization, also known as weight decay, shrinks all weights smoothly, preventing large values from dominating. In deep learning, L2 is used more often because it helps stabilize the model without making it too sparse. Early stopping is one of the simplest and most effective ways to prevent overfitting. Here's how it works. Imagine you're cooking a steak. You don't want to undercook it, but you also don't want to burn it. So what do? You watch carefully and take it off the heat the moment it's perfectly done. Early stopping works exactly like that. Instead of training your neural network for too long, you monitor its performance on a validation set. The moment the validation loss starts getting worse instead of better, you stop training right at the sweet spot before overfitting kicks in. Batch normalization is another powerful regularization technique, but it works a little differently. Instead of reducing complexity, it keeps the network stable by making sure each layer gets properly scaled inputs. Think of it like a DJ mixing audio. If some instruments are way too loud and others are too quiet, the song doesn't sound right. Batch normalization balances the inputs at every layer, ensuring that learning happens at a steady rate and preventing the network from becoming too sensitive to any particular feature. Let's say you're building an image recognition model to classify pictures of dogs and cats. If you don't use regularization, the model might memorize specific details of the training images, like the background, lighting, or specific textures of fur. So when you give it a new image, it might fail because it was relying on details that had nothing to do with whether it's a dog or cat. But if you apply dropout, L2 regularization, and batch normalization, your model is forced to learn the actual distinguishing features like ear shape, eye position, and nose structure instead of memorizing specific training examples. Regularization in neural networks is not optional. It's absolutely necessary if you want a model that actually works in the real world. Dropout prevents over-reliance on certain neurons by randomly disabling them. L2. Regularization, weight decay, prevents weights from growing too large and keeps the model balanced. Early stopping makes sure you don't train too long and start overfitting. Batch normalization keeps input stable so the network learns efficiently. And now that we've covered how regularization keeps neural networks under control, the next big question is, how do we apply it to tree-based models like decision trees and random forests? Because when it comes to tree models, regularization looks completely different. But trust me, it's just as important. It is time to moving into regularization in decision trees, and this is where things get really interesting. Because unlike linear models and neural networks, decision trees have a completely different way of